Okay, after 10 minutes of technical difficulties due to a cable, I guess we can start. What I'm going to talk about today is QuickChick. So QuickChick is a property-based testing tool for Coq, and basically it's a power tutorial on how to use it, how to be able to find bugs during your proofs and stuff like that. So it's very much in the style of Software Foundations in this these files. So stop me for anything. If I'm assuming something too much because you don't understand some bit of notation, or if I'm glossing over something that you want to ask more, just feel free to stop. And just a quick show of hands to sort of gauge. How many are familiar with Coq? Yep. How many are familiar with testing in general? Okay, yeah. Type classes? Okay, cool. That's sort of what I prepared for, so that's good. Okay, so of course you need to import some things. Like you can look this up to see what it is. The point, the question I almost always get whenever I start talking about random testing in Coq is why, right? Like we're proving things. Why do we need to test them? And the answer is, after you prove something, you don't need to test it. That would be sort of a waste. But as you're proving things, it might be really good to know that something is true before you embark on a proof, and you realize a month later that there is some weird edge case that you didn't find. So how does QuickChick work? Well, let's say you have a program. Here is a remove function, which takes an X, a natural number, and a list, and removes it from the list. And here is a specification for it, which says that after you remove something from the list, then it doesn't exist in it, right? So here's a program, here's a specification for it. Can anyone spot a bug immediately? Probably, it's like 5 lines. But wouldn't it be easier if someone else just told you, well, if you run this a bunch of times and shrink it a bit, which we'll explain what it means, if you call it with the number 3 and the list 3,3, then there's a bug. And then you go to the then case, which shows that you're not removing it from if it already exists, right? So you don't remove it from the tail, you don't have a recursive call. Now, is that a bug in your remove? Is that a bug in your specification? Who knows? But at least you know where to start looking for the discrepancy, right? So that's all QuickChick does. If you give it something that it can run, and something that tells it how it should run, in terms of an input-output specification, it will just find bugs in many cases. Now, of course, it's not as simple as that, like how you generate stuff, how you link everything together, and the more complicated your properties become, the more effort you might have to put into the generation process. But this is what we're gonna do today. Like we're gonna cover how to get these stuff to work seamlessly. For example, you might want to write things in a more declarative manner, right? In Cog, you sometimes, let me move that further up, sometimes write things in propositional specifications, inductives, right? For all X and L, X is not in the resulting list. But for now, if you try to quick check this, it's gonna say, well, that's a prop, I can't check it based on some type classes. We'll see how you can check that easily again by the end, but in general, you want something that can run so that the testing tools can be like, I run this, I got back false, here's the discrepancy. So for property-based testing, there are 4 ingredients. An executable property, so like the remove above instead of this one. A printer, you need to show counterexamples to the user. A generator, you need to generate random inputs. And a shrinker, which we'll explain later, which is the way we saw the counterexample be 5 and 5,5 instead of 5 and a huge list that happens to have 5 twice. So it minimizes the counterexamples in order to get more concise feedback to the user. For all of the latter 3, printers, generators, and shrinkers, QuickChick uses type classes to sort of automate things. So in Calc, you can define type classes, and here's the one that defines a type class for show. At its core, it's just a way of saying that for anything of type A you give me, I can provide a function that converts it to a string, right? And then you can write instances for that. So, for example, you can have colors. I don't know why Software Foundations always uses colors as the main inductive example, but let's assume colors are red, green, blue, and yellow. Then with this indentation, which is becoming more and more annoying as top versions increase, you can write an instance of show color. So you're defining something of type show color, which is a record with a single function, the show that we had above, and converts it to a string, right? Okay. This export is it's a recent addition. It tells it that whenever you import this file somewhere else, you're also importing this instance. Because the way type classes are implemented is basically two things. You have a record, which is defined somewhere, and you have a hint database somewhere that allows you to search for these instances whenever you need them. And therefore, if you want to do something like show green, it will just figure out by itself that, oh, this show color instance exists somewhere. No, we didn't link that to anywhere, and it just computes and gives you back green. Of course, writing these things is extremely tedious, and I wouldn't want to write show color for every single thing I write. So QuickChick does provide automation for these things. Derive show color is defined. And if you see what it got, like it's basically exactly the same thing. Like you get it for free. And this works for basically everything where you would expect the normal inductive hypothesis to sort of work. Right? If you start doing weird mutual inductive things or nested inductive things, it's probably not going to work. It might, but not guaranteed. But for anything where you get a reasonable inductive hypothesis, you'll get a reasonable show. Okay, so that's printing. Very simple. You derive show. If at some point you want better printing, you'd have to write the one instance by hand so that you can print lambda terms or whatever else you want. But to get started, you can just derive things. Now, generators. Ignore the M word. I'm not going to touch burritos or anything like that. But basically, there are two core components of generators. You can create a point generator. So return gen allows you to create a generator that only produces the same thing. So if you want to sample return gen 42, that will generate 42 randomly every single time, because that's what you told it to do. And bind gen is a way of combining different generators. So if you give me a generator for type A and a function from A to generator of type B, I get back a generator for B. So if I have a generator, so bind gen takes two things, a generator for something, return gen 41, and a function that given an x does something else, I will also get 42 a whole bunch of times, but this time I'll do it by sampling 41 a bunch of times and then returning the distribution x plus 1. So this is just a way of combining generators. We haven't done anything random yet, so like we need one more thing to make everything work. And the one more thing that we get is primitive generators for a whole bunch of things. And the most primitive one is choose. So now, if you ask what the type of choose is, it's going to say that it takes a pair of natural numbers and returns a generator for natural numbers. But that actually works it just monomorphizes it under the hood, and it's for any type in a type class that supports it. So it can work for Booleans, it can work for naturals, Z, like anything you probably guess that it's ordered in the standard library of Calc. And the way it works is if you sample from something like choose 0, 10, then you get a whole bunch of numbers from 0 to 10 inclusive, right? So you'll get things like 0, you got 10, and you'll get a whole bunch of distributions in there. And that's one of the most easy combinators to start playing around. So if you wanted to generate the X that we saw before for the list, you can just use choose with some range, and everything works out. Now, one caveat is that everything that is happening here is sort of delegated to OCaml for generation and printing and everything like that, because Coq doesn't support random numbers. Coq doesn't support input-output. So this sample command that I've been using, and the QuickChick command as well, extracts things to OCaml and runs them, which means at some points you might get exceptions from the OCaml side here. So if I try to sample something on the other way, you might get fatal errors, which are choose called with unordered arguments, right? This is something that's a bit weird about trying to do things in Coq, which is the type of choose right now is, let's say, a pair of natural numbers to a generator. But Coq is a total language. So you would either have to make that an error in Coq, and then it's completely hideous to use everywhere else, or you do that hackiness and you allow OCaml to make it no total. So if anybody has any ideas how to reconcile those, I'd be happy to talk. But in general, some of the errors in QuickChick are going to happen on the OCaml side, and hopefully the errors explain themselves in terms of what's going on. And here it just says that choose was called with unordered arguments, which, yeah, we did. Okay, so we have return, we have bind, and we have choose. In order to test the thing we saw in the intro, we also need some way of generating lists. How are we going to do that? Well, there is this list of combinator, which takes a generator for A's and produces a generator for a list of A's. So basically, we are repeatedly calling list the inner generator for the elements and creating a list. So if we sample for list of 04, we'll get some random list, all of whose elements are between 0 and 4, and their length stack. Right? So we just repeatedly call this generator to generate a bunch of stuff. There is another combinator for lists which fixes the length. So vector of takes a natural number and the generator for the elements and produces the list. Now, based on this type, what the natural number is doing is creating the size of the list. So if I sample vector of 3, choose 04. All of the lists I get here are of size 3, right? Every single thing. So, which sort of begs the question, how does this decide the length of the list? This is obvious. What about that? And the answer is that QuickChick has internally a size parameter that it has access to, and that every single generator can access. And it increases it more and more as your testing goes on. So we'll see an example of that in just a tiny bit on how to use it. But basically, this G hides not only the randomness from you, but it also hides some size information that you have access to. Yep.
Why do you choose to use the upper bound type of strategy as opposed to just like randomly choosing between nil and ones and just assuming it will eventually work?
Good question. We're going to see exactly that with trees in a bit. But basically, the general idea is that if you want to do exact size generation, like if you were to treat the size for weird data types as an exact thing, it's very hard to do to guarantee exact size generation. So if you treat it as an up to this size, then the semantics of your generators are much easier. You can just fail at some point and be like, oh yeah, just return a node here, everything works. Exact size things are really hard to get with a good distribution in the presence of preconditions. We'll talk about that. Okay, so we have primitives and we have lists, but whenever you're working in Coq, you're usually just defining your own data types, right? You're defining your trees, your lambda terms, your whatever. And there are a couple of combinators in QuickChick that help you generate those. The first one is LMs from elements. It takes, basically what it takes is a list of A's and produces a generator for A's, but selecting from that list. And again, we're annoyed by Coq because what would happen if the list is empty? You still need to generate an A, and the A you're generating is this default element. So there's a default element in a list, and you return the whole thing. You'll note the underscore. The underscore is part of the naming scheme of QuickChick, which is that the variants that have a default element that is usually unused have this underscore because they're the thing that Coq needs to define. But there's convenient notation to allow you to get away from it. So if you ever provide an explicit list, like X or XY or anything like that, you can just write LMs without a default element, and it works. And it extracts the first thing to be the default element that it ignores after, right? So if you sample gen color now, you'll get a whole bunch of colors, green, red, blue, whatever. Roughly uniformly distributed, right? There's nothing in this list that is that should be more represented. But that's not necessarily enough, right? If you want to generate enumerations, LMs is fine, but if you want to generate lists or trees by yourself, you need something more complicated. You need a way of combining generators, not elements. So let's look at the main data type that we'll be looking at today, which is trees. If we have an inductive of trees, this is standard binary trees in Coq. You have a leaf, you have a node, and this is the standard trick to make sure that the A is an implicit argument and I don't have to write list and the type everywhere. And we can define a show instance. We can either define it ourselves or we can derive it. And that has basically the exact same structure as this. And in fact, it's even smarter with parenthesizing things, so I'll just ignore this. Now, the first combinator that combines different generators is one-of. Just like elements, you can ignore the first part. It takes a list of generators and gives you back a generator for A's. So as you can probably assume from the type, it picks one of the generators from the list and uses that to sample A. So it combines a whole bunch of different generators. So how would we generate trees based on this? Well, we could do what Anders said for lists. We can either generate a leaf or generate a node recursively and hope it terminates. Well, let's write that. And the fact that I have fail at the top of it, you should probably tell you that this won't work. And yeah, like Coq cannot guess the decreasing argument of fix. I'm writing a fixed point that takes a generator for the element and either returns a leaf or uses the generator to sample. I should be using bind here, but let's rewrite that in a more convenient way. Bind gen. I'm generating an element. I am generating a left tree. I am generating a right tree. And then I'm combining all three by returning node XLR. So this is usually the way you would use the bind in red that we defined above, and there's a notation that I'll get to right after. But basically, you are generating a tree for the last one, generating the right tree, and then combining them all together. And now, if you try this, Coq will complain that it cannot guess the decreasing argument because everything in Coq has to be terminated. And Haskell would love you to define this, and it's going to be fine, and you could sample it. But here, Coq's termination checker actually helps you because if we were allowed to run this, the expected size of the tree generator is actually infinite. So you will get leaf 50% of the time, leaf, maybe a couple of nodes, and then at some point your computer will crash because it will start generating too large things. Yeah, so what do we do? Well, the standard solution is to bound things on the top by a size. So you give it a size parameter, a natural number. And in QuickChick, the idea is that this size parameter is an upper bound on the depth of the thing you are generating. And that's mainly because it's very easy to then recursively do things that satisfy the termination check. In Haskell, it's usually common to denote number of constructors and then divide it by 2. But dividing by 2 here won't work because Cox termination checker. So what we're doing here is exactly what we were doing before, with the one difference that instead of immediately choosing between returning a leaf and a node, we are first matching on the size. If the size is 0, we're only returning leaves, and this is why we have the up to bound on something. And if the size is more than 0, you have a choice. You could either generate a leaf or generate a node. And this, as you can guess, works. You can, for example, generate random trees of size up to 3 with elements between 0 and 3, and you'll get a distribution that looks like this. And if you start looking at it, it's like leaf, 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 and a bunch of nodes. And that makes sense, because like 50% of the time, you're generating a leaf. If you're testing a property with trees and 50% of the things you're generating are leaves, probably wasting a bit of effort, right? It's not really what you want to be doing, testing the same thing over and over again. So for that reason, there is another combinator that allows you to control distributions a bit more. Instead of having a uniform distribution, you can skew it. And that combinator is called frequency, and or freq. It takes a list of natural numbers and generators and selects from them. This is SS-reflect stuff. And the first element is a default generator that just ignores with notation. So what's the idea here? The idea here is that instead of generating leaves with uniform distribution, so 50% of the time you generate a leaf with 1 above, the fact that we're using 1 in size as the weight tells QuickChick that it should generate leaf 1 out of size plus 1 of the time, and it should generate a node size out of size plus 1 of the time. So in the early stages of generation, when you have a lot of size to work with, it skews generation towards generating nodes. And at the end, when your size is 0, it basically says, no, just generate a leaf, stop doing anything else. And if you try to generate something now, you'll get much bigger trees, right? So you'll get a leaf. It's still possible to generate one, but it's only 1 out of 3 or so. So you'll get bigger trees. Which for some reason is better for testing, and we'll talk about that in a bit. And I think that's basically it on the basics of generation, right? So you write a generator using these combinators, and QuickChick finds your counterexamples for you. Of course, everything that we've been writing so far is also automatable, and we'll get to that. But before that, let's actually find a bug. Let's actually write, here is a mirror function for trees, which is just mirroring the left and right subtree and swapping them. And let's assume we have structural equality of trees, which is just running down the structure of T1 and T2 and comparing the various things. One property you might expect from mirror is that it's unipotent. So mirroring a tree twice yields the original tree. That is something that should work. If you QuickChick that with some generator for trees of size 5, QuickChick will quickly say, okay, we run 10,000 tests, that looks good, you're fine, start proving. But if you had a property that is wrong somehow, let's say that instead of making it mirroring a tree twice is the original, then mirroring it once is the original, which requires quite a deep tree, right? Like you need a node and then an inner node, and those two don't have to be the same. Well, you can generate something. And here's a counterexample. If you start looking at it, it found it in one test. It just generated a random tree and it was mirrored. But what is the counterexample? Right? Like this entire thing is not something that is useful to identify what goes wrong. Which is why QuickChick has shrinking. What is shrinking? Shrinking or delta debugging is basically a way of minimizing that monstrosity that we had above to something that is tractable. To basically node zero, leaf, and leaf on the other side. Something tinier that you can actually work with. And the idea is that users provide a way of creating elements that are one step smaller. So shrink is So for trees, for example, which is the easy one, you have to provide a function from a tree to a list of trees. And the way it works is everything in that list is somehow one step smaller. So leaves are already as small as possible. You're not going to minimize them. Nodes, you can minimize to the left subtree, to the right subtree, or pick a way of shrinking either of the three arguments. Right? So if you shrink x by a bit, then you get another tree. If you shrink the left subtree, you get another tree, and so forth. And all that does is that if you shrink, if you use a different combinator that allows you to also specify a shrinker, you get back a much more readable counterexample, which just contains actually one of the two minimal ones. Right? It's I think there we got the other one. So there's one counterexample with leaf on the left and node on the right, and one counterexample with node on the left and leaf on the right. And you get one of the two because they're both the best thing you can do in the best first approach. So what shrinking does is that list of options that we applied, once you find a counterexample, you apply that list, you traverse that list. If you ever find a counterexample again, you keep going from there. So it's the best first search for something smaller that still fails the property. And now we're putting it all together. There are two type classes. There is gen and gen sized, which are type classes that contain generation. So let me, oops. What am I doing? Okay, print. So if I print gen, like gen is a type class that contains a single function, g of a. So it allows you to, it tells you that you can generate elements of a. And gen sized is a type class that, in addition to that, takes a natural number. And this natural number is like the sized version for the tree generator that we wrote, so that you can write between the two. And you can connect the two of them automatically, so the only thing you need to write is gen sized. And the only thing you need to write is a shrink type class which has a shrink function. Which means that if you have these instances, so if you tell it that to generate a tree, you need to generate a size tree, and to shrink a tree, you need to use the shrink tree function, then you can automatically QuickChick faulty mirror P, which allows you to find the same bug immediately. Of course, it would be extremely annoying if you had to do this for everything, including these very small things. So before I get to collecting statistics, the first thing that we're going to look at after is QuickChick's automation, which allows you to derive arbitrary for a tree. And that defines two functions, gen size tree, which is basically the arbitrary function that we wrote. So it gives you the generator for free. A shrinker, which gives you a shrinker for free. And a show, then you can derive a show instance. So basically for every new data type that you're defining, you can just derive arbitrary, derive show, and everything that we saw above is produced automatically for free, and you can use it. So the reason I've been going through all of the combinators to, one, for you to understand what this generates under the hood, and two, because the next thing that we're going to do is going to require sometimes to understand what's going on so you can fix it. Okay, so before that, let's talk about statistics. So earlier in the tutorial, I claimed that the generator that we had that used one-off was bad because it produced a lot of leaves. And the only reason I said, the only evidence I provided for that was I looked at the output list and I saw a lot of leaves. So my vibe said it was very leafy or something. But you don't have to do that. Whenever you're doing testing, you're generating all of your inputs, so you can collect statistics about them. So for example, here is a size function for trees. It takes a tree t, and returns a natural number. So basically, this is just the number of nodes in the tree as a function. And you can write a dummy property that just allows you to collect statistics for your generators. How? Well, if given a generator from a size and a generator for natural numbers and a generator for trees, you call the generator, create the tree, and then your property is just true, so you're not testing anything. But the interesting part is this collect mechanism that tells you that, oh, as you're running it, I want you to collect the size of the generated trees. So if I call this property with QuickChick for the original generator that used one-of, you'll see that roughly 50% of the time you're generating a leaf. So like this is almost statistically significant. Out of 10,000 tests, 5,000 are leaves of size 0. On the other hand, and worse, there are very few things of higher sizes. You're not getting everything that you want. On the other hand, if you're getting the sized version with frequency, you'll see, yes, there are still quite a few leaves, but there's a very healthy distribution of other weights as well. So our distribution is now much more uniform in the size of the generated tree, which is generally a good thing. You don't want to be generating only leaves. Yeah. So that's the first of the 3 parts of the tutorial, right on time. Now, basically, we talked about the very basic usage of QuickChick. You can generate data, you can shrink data, you can print data, and then you can test properties like the one we saw in the beginning, the remove P. But you have to sort of write this yourself. And this is not a very interesting property in that it doesn't really have any fancy constraints on X and L. If you're going to do PL meta theory in Coq, you're usually going to have much more constrained inputs, right? If my term is well typed, then it takes a step or something, right? Progress, preservation. And then if you were to generate inputs based on type information, well, you're not going to have a good time because they're never, if you're generating random lambda terms, they're never going to be well typed. So we need a bit more machinery, and that gets us to more of the automation that QuickChick uses. Now, again, I'm going to be just using trees because the entire tutorial is based around trees. And, oops, let's retract. And right before, these are just simple binary trees. We have leaves, we have nodes, and we have the arguments made implicit. Instead of writing a generator and the printer and everything, I'm just using derive, so I'll be using the automation more and more. And all this is doing, it's defining the thing that we were seeing right before.
However, is the derive mechanism being with this frequency skewing?
Good question. So the weights it gives by default are 1 and 1. But you can hijack that without actually tweaking it. So you could do something like, assuming I remember the incantation correctly. So leaves have size 1, and nodes are based on size. Tree. I have it somewhere, which is in the BST. This looks identical. Yeah. This should have worked, which makes me not confident that the one in the other one worked, even though I compiled it. Okay, that seems to work. Yeah. Like there's some import I'm missing, probably, but an incantation like this allows you to tweak the size of the thing you're generating in order to get the distribution you want to skew it more. Should this be S3? Yeah. So let's ignore the sizes for now, and we'll get back to it. Now, to decide propositions like the remove in that we saw earlier, well, there's type classes for that too. And we're going to use SSReflect. I think that, can I do it now? Anyways, so SSReflect has this decidable property, this decidable function, which is a way of classifying propositions as if you give me a proposition that is decidable, then you either can give me a proof that it holds or a proof that it doesn't hold. So it allows you to classify these propositions. And QuickChick has a type class around this decidable that allows you to classify various P's as decidable or not. And then you can use that to decide things for QuickChick. And there is also a partial decidability type class, which takes a natural number argument as fuel. If it can't decide whether the property holds or not, then it will return none. If it can definitely decide if it holds or not, then it returns some true or some false. That's the idea of partial decidability. And these are supposed to be monotonic in the sense that if you ever return some true or some false, you should return the same thing for every higher number. So it allows you to encode that, well, I would need more fuel, more iterations to decide whether something holds or not. And then for both of these, there is notation. Basically, if something is decidable, you can use a single question mark to convert it to true or false. And if something is partially decidable, you can use a double question mark with a default, with some fuel that you give it to decide, to try and decide whether it holds or not. The most common use of DEC is usually for equalities, to make equalities between things Boolean, and that's also a type class by itself. So it allows you to decide whether two things of type A are equal in a decided fashion. And for this in particular, there is a very convenient tactic, again included with QuickChick, that allows you to not do anything other than define that, yes, trees of various A's should be equal, and that is happening by decidable equality. And this sort of replaces the entire EQ tree that we wrote manually before to check for mirroring. Right? And you just write this, and now you can write mirror again. And now faulty mirror P is just this line. You don't write EQ tree, you just add this question mark, which the way it binds is looser than you expect. So this is the way you should read it. So mirror T is equal to T prime. You add this question mark, and because equality between trees is now decidable based on the type class we defined above with the one line, now you can actually test the faulty mirror P, which is what we couldn't test earlier on in the chapter, right? So if you give me a decidable or a DEC opt instance of something, then you can use faulty mirror to decide. Of course, it's not only equality, and a lot of the time you'll have other preconditions. And basically the rest of this tutorial is about handling those. Here, the first thing I'm going to talk about is balanced trees. So what do I mean about balanced trees? It's a very simple inductive that defines when a tree is balanced at a particular size. So let's ignore B1 for now. A leaf is balanced at size 0. And if you have a node that is balanced, if you have a left tree that is balanced at size n, and a right tree that is balanced at size n, then combining both into a node has you a balanced tree at size n plus 1. Now, if I don't include B1, that creates perfect trees. That creates trees that are completely full. If I have two constructors that allow leaves to be balanced at both 0 and 1, it allows you to have trees that are balanced, almost balanced, almost perfect trees. So things like, how do I write that easily? Something like node 1, node, let's ignore the numbers, node, leaf, leaf, and leaf. This is a balanced tree at size 2 because it's almost like the size of any level of any path differs by any other path at most 1. That's the thing we're guaranteeing with this balanced. For example, this is used if you want to have something like ADL trees or red black trees where balance is one of your considerations, because things should be as balanced as possible. In ADL trees, red black trees have the difference variant. But let's encode a naive insertion function that always inserts things on the left and clearly breaks balance, right? So here is an insertion function. What that does is it inserts x on the left of the tree, on the leftmost path, either at the leaf or goes down left until it finds something and inserts. So if I repeatedly insert these things, I will break a balance. Like if I start with a balanced tree and I start inserting things to the left, well, pretty soon, basically after 1 or 2 iterations, it's not going to be balanced. But if we wanted to write that property, we'd need a way of checking whether something is balanced. And what we have up here is an inductive, right? So how, like, you'd either have to write a function that checks whether something is balanced, repeating effort, or you'd have to not write your balanced and write it as a function to begin with. However, as of last year, you can also derive decidability predicates, partial decidability predicates for various things that you're defining. So the balanced inductive that we saw, what you're saying is, okay, give me a partial decidability checker for it, and you get back an instance of the type class for that. So if you want to see what that looks like, actually, before you see what that looks like, let's compute with it. What do we get? Well, if you want to check if a particular tree is balanced at height 1, you can just use the double question marks, check it, and it will say, yes, that tree is balanced. Well, is leaf balanced at height 2? No, some false. But of course, in order for this to be terminating in an automatic fashion, it uses size in a meaningful fashion. So it can decide whether something is balanced if you don't give it enough fuel. So here I'm trying to see if a tree that actually is balanced at size 3 is balanced, but I give it too little fuel. I give it only 1. And in this case, it's going to return none because it doesn't know yet. So what does this do? Let me print dec opt balanced. It's not a pretty decider, as you can expect, because this has to be as generic as possible to make things work. But the main idea of what it does is that it checks for 3 things. It basically checks, is it a leaf? And if it's a leaf, is the natural number 0? Because that's, let me take you to balanced. So how would you check if this function worked, right? Well, is this a leaf and then number is 0? Is this a leaf and the number is 1? Or, which is exactly what we get here. Is this a leaf and the number is 0? Is this a leaf and the number is 1? And you're getting 1 for each constructor. And the last one, which is a bit bigger, it's basically asking you, well, is this a node? Is this a successor? And if it is, then is the right thing balanced at size R and is the left thing balanced at size R? And that's exactly what it's doing here. It's calling the inner thing recursively. So it's not doing anything extremely smart, but you get it for free and you get a proof that it's true for free if you want. Yeah, and what that means even more is that, wait, here. So you can write properties that include balance. So for example, you can write a property like all trees are balanced. Very obviously not true. You can define it and you can QuickChick it immediately. You don't write anything else. You have the generators that you wrote at the very beginning. You derive the checker for balanced, and you just QuickChick it and it says, yeah, here is a tree that is not balanced, because obviously. Now, what about the other way around? What if the property that you have for ABL insertion, for example, is that if a tree is balanced, if a tree is an ABL tree and you insert something in it, it would remain balanced after all the rebalancing, which would mean that you need to generate balanced trees. But as we just saw, not all trees you generate are balanced, and you don't want to filter them because you would get a lot of them that are unbalanced. So what QuickChick does is it allows you to also derive a generator that is constrained by something. So you can write this incantation, which is the type class for constraint generation, and you tell it what you want to generate. So the property here is that, the idea here is that n is universally quantified. It's an input to your function. So this would generate trees T that are balanced at some height n. You can define that, and that generates, first of all, an instance of a type class that we're just about to see, that contains a single function, arbitrary size as t, from natural numbers to a generator for option A. And the idea is that everything here satisfies this P. So let's see that in action. You can sample trees that are balanced at 1. So this is the way of calling the function above. And you add 4 trees that are balanced at type 1, and you'll get back some leaves and some nodes. Those are the things that are generated balanced. And if you ask for higher things, you'll get bigger things that are balanced, and sometimes you might generate none because it might fail. But the main idea is, this printing is very annoying, but if you just take one of these, and you manually try to see where things line up, well, this is a tree that is balanced at size 3 because there is no. So there's no way you would generate this on accident and only use things on size balanced of size 3. But what the generator does is, again, not something particularly smart. So if I go back to the balanced, if you look at what it does, it basically picks a way of generating trees that's such that they satisfy one of the constructors. So how would you generate a balanced tree based on this inductive, right? Well, one choice is, if my natural number is 0, then I can generate a leaf. If my natural number is 1, then I can generate a leaf. And if my natural number is a successor of something else, I could try recursively generating a left tree that is balanced, a right tree that is balanced, and then combining the two together. So And that's exactly what the generator does. It's a very, very naive way of viewing things. It checks, there's one generator that checks if the number is 0, in which case it gives a leaf. There's one generator which checks if the number is 1, in which case it generates a leaf. And there's one generator, which is a bit more complex again, which checks whether n is a successor of something, in which case it recursively calls the generator that it's defining to generate a left and a right subtree before combining all of them into a node. Yeah, so the one thing that's different from before is that it's using a combinator that we haven't seen, which is called backtrack. And yes?
Where are the nuns coming from?
Exactly. So the type of the generator that we're defining is something that returns an option tree. And the idea is that, well, if I were to write a generator that produces only balanced trees by hand, I could probably just combine all the different cases together, right? I could say, okay, if n is 0, then I'll generate a leaf. If n is 1, then I'll have a choice between generating a leaf and generating a node or something. And if n is more than that, I would just do things. However, there is nothing in inductives that allows you to, that specifies that you have to have this kind of structure. So something that handles any inductive you give it automatically is much more naive than that. So what it's doing is, can I use B0 to generate things? And if the number that you give me below is like 3, like we gave it, then no, the answer is I cannot generate a balanced tree using B0. So in that case, the result of the function is going to be return check none. But because we're using this backtrack combinator, which is basically frequency but with options, what it's going to do is, if an inner generator returns none, it's going to backtrack and pick a different choice. So you're paying a bit of local cost to sort of not do global reasoning about which cases can happen at the same time. So the naive algorithm that's behind this is, pick one of the constructors, try to generate for it. If you succeed, great. If you don't succeed, pick another constructor until you run out of options. It's nothing crazy, but it works quite well a surprising number of times. Yep, and now that we have both of these, we can generate things that are balanced. And so, for example, we can use both the generator that we define and the checker to make sure that QuickChick has done the right thing. So this is the part that is not yet easily, hasn't been automated in QuickChick, which is basically, how do you put the different things that you get for free together? So let's say we want to write a property that says that the generator for balanced trees produces balanced trees. We already have access to something that generates things. We already have access to something that generates, that checks whether things are balanced. And now we just need to put them all together. So how do we do that? Well, we just need to write a property. Let's say our fuel is 10, just arbitrarily. And in order to check that, we need first to figure out what trees we're going to generate, what balance of trees we're going to generate. And for that, we need to create an arbitrary number n. How do we do that? Well, for all is a combinator that if you give it a not result, right? It's one number 5 to something. If you give it a generator for some time a, and then a function from an a to something that it can check, it constructs a property that QuickChick can check. So if you give me a generator for n's, the rest of it is a property that you can check. Okay, so we're telling it that it generates an n by choosing between 0 and 5. It generates a tree T by generating a balanced tree with a particular amount of fuel. And this combinator is the same as the one above, with the only difference that it actually expects something from option results and unwraps it, right? So because the generator that we derived for trees is an option tree, it returns an option tree, then this combinator will unwrap that option internally, and you don't have to do it. So you're generating an N, you're generating a tree, and then you're checking whether it is true based on some amount of fuel, right? So the annoying part for now, eventually that's going to be automated again, is figuring out the different hyperparameters to this, right? So why are we using fuel to be 10? Why are we choosing the arbitrary number to be 0 and 5? The property I would like to write here is something like this. For all n and t, if I gen balance n and t, then that thing is balanced. Something like that. So even worse, actually, I would like this property, right? Like this is the property I'm writing. Like if I were in the middle of a proof, generating balanced streaks and checking whether they're balanced is the equivalent of this. But type classes are not strong enough to handle these kinds of dependencies yet, right? So what we would like is generating things for tree, generating arbitrary ends so that you can use that, and then checking whether that holds. So that doesn't really work yet completely. So you have to write something like this manually. But if you do write this manually, you get 10,000 tests passing, and therefore everything generated by this is indeed balanced. Yes.
So, but as a user of this, I hope that I would not have to write tests to check that my testing framework is generated correctly.
Yes, of course, of course. This is just this is not the case study yet. We'll get to that. But like this could be any other property that you wanted, right? This could be, and we'll talk about that immediately, I guess. So the property could be something like progress or preservation for all gamma et, something like this. Typed gamma et, step e prime typed gamma e prime t, right? Like that's maybe some way that you would write preservation, right? And the question becomes not preservation, preservation. So the question would become, how do you test this with what QuickChick gives you, right? What QuickChick or anything like that would give you in Haskell is, okay, you can get generators for these, and then hope that it's well typed and hope that it steps to another. Like, that won't work. What QuickChick gives you is you can, we can actually just do this right now. I've not prepared this, so that's a very bad idea.
Then you know you need to do it on the second background.
Yeah, exactly. STLC, perfect. Do I have STLC stuff somewhere? I probably do. Have an example. Not stack compiler, STLC. Is that the one I want? Give me one. I just want the basic definition somewhere. Examples, fuzz, no. Let's write them. How hard can it be to write STLC? Okay, we have inductive terms, types first. So what are our types? We have arrow, we have some base type, and we have an arrow type. Okay, come on, there's no way I don't have that as an example. benchmarks. Yes. Okay, I do have that as an example. Just realized it would take way too long to actually write that whole thing. Okay, yeah, this is readable-ish. So you have types, and types are natural numbers or arrows. Fine. You have decidable equality between types. That would make sense. And you also have arbitrary and show. And there's also this enum size, which I haven't talked about, but it's enumeration. Okay, so we're deriving everything that we did so far, like everything I've been talking about in 5 lines instead of 150 in an hour. Then you have terms. So let's say our variables are natural numbers, and I don't mean the brown, I just mean like 0 is my identifier. And I have constants, which are natural numbers, identifiers, application, and abstraction. We can derive arbitrary for that, the completely naive one. And we can also define environments, lists of types. And the first thing that we would have is some way of combining environments to types, right? So when does a particular variable bind to a particular type in an environment? Well, if it's the first 0 binds the first thing, and successor of something binds the next thing. So actually, I am using the graph, right? In this. But because 0 is the first element of the thing, and successor of x is the next index in it. Okay, and now we can derive things that allow you to do various stuff. So we are deriving arbitrary size such that for bind GXT. So this will generate variables whose type is t in a given context. And this will do a similar thing where it will give you the type of a variable in a given context. So this does the opposite. And the last thing is you can write a checker that checks whether an expression has a given type in a context, bind, where their variable has. Yeah. So all of that for free. Then you can write typing. Yeah, this was a good idea. I should not have written that on the fly. What do we have typing? Well, identifiers. If a variable is bound at a given context, then the identifier of that is correctly typed. Constants are always typed in natural numbers. Abstraction, the standard thing, you're extending the context with the type of the abstraction, and you're creating an arrow type. And for application, if you have an application, then it has type 2, T2, only if the argument has some type and the function is of an arrow type with the result, right? Here I'm writing type off manually, but I think we also have later on something that doesn't do it. So this is a function that type checks a particular expression, right? Identifier gives you whatever the nth thing in the environment is. Const gives you a number. Abstraction type checks the abstraction and gives you back an arrow. Application type check both, make sure that they match. Done. So I'm not doing anything very fancy here, but I'm just glossing it over because. So the next things are a whole bunch of generators, which I'm going to ignore for now, because that's not what I want to do. What I want to do is show that you can derive these, right? So I'm generating expressions that have a given type in a given context, generated for free, well-typed parameters. You can derive a type checker, essentially, which enumerates the possible types for t for an expression in a given context. So the type function that I just showed, you can get it for free. And you can check whether a variable has a given type in a given context. So you get a type checker for free, just by using QuickChick. All of the things in the middle that I defined are not like, this is in a benchmark module, so it just wants to compare the performance of the handwritten ones versus the other ones. So even if I don't write any of these, I still get these for free, right? This is all you need to write. All the different ones are just for benchmarking purposes. So you get a generator for well-typed terms, you get type inference, you get type checking, And this type checking uses the type inference because it automatically figures out how to do bidirectional type checking, essentially, under the hood. Then you can derive like call by value semantics, like we have values which are constants and abstractions. You have substitution, and it has some bugs in it if you want. You can include bugs, like this is the stupidest bug possible. Like you're substituting, I guess this is not, this is a bug that I could have actually have done. Like you forget which one you're substituting and which one you're substituting for, or something. And this is a bug that if you've ever written anything in the Brown, you have done, which is like not lift something or forget to shift. There is stepping, and you can see how it steps. Printing, in order to actually print things, that's the one thing you actually write by hand, because like printing lambda terms in a pretty fashion is not something that you want to should be showing arrow blah 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 all the time. But let's ignore that. And okay, here are preservations, right? We have a whole bunch of different things because we're benchmarking a whole bunch of different things. Let me include the things again. Let me add those back in because they're needed for various things in the bottom. And we were around here. So you define your property, for example, preservation, as the one you would want is something like this. You would write something like this. You would write a checker that says that if you have a term and a type, and you step the term, then the resulting thing also has the same type for some fuel. And this is not something, normally what you would write at this point is your preservation as a theorem, right? At this point, you would write exactly what I was writing above. So gamma E T T prime, typing, maybe you'd even put it with nil, but whatever, gamma E T, step E equals E prime, typing gamma E T prime. E prime T. Okay. Option term. Okay, sum. Whatever. You'd write something like this, right? And ideally, like after you've defined generators and enumerators and everything and checkers for this, the rest is at the same time very easy to write and also very hard to figure out what to write. Because how do you test this property? Right? Like this is a research question almost, right? Like I'm giving you this without access to everything else I've defined. How do you test this? Well, the naive thing is, okay, generate everything randomly and hope. Yeah, like for this, it's never gonna work. So me looking at it right now, and if you do anything with testing, you as well, after like a very bit of practice, could be like, okay, I know that in order to satisfy this, I'll need to generate terms that are well typed. Well, I know that this is deterministic, so I can just run this and get the E prime. And then I can type check this. So I derive these three things I said above, and I put them all together to find it. Automating that intuition in order to get from the 10 lines that I'll show you that you'll have to write to test this to no lines is very hard. We still are most of the way there, but yeah, next time I give this tutorial in 5 more years, hopefully it will be easier. So what you write is something like this. So here is a checker for the result of that function. Right? Typing GET, I guess this is nil because my preservation has new empty context. But what this says is that if you give me a term and a type, if you step it, then you get some E prime, and that has to be the same type as the original. Right? And now you have to specify how you're generating E and T for that, which means let me do this. Which means that here is the property that uses that thing. You specify you generate T, which is, well, I'll just generate an arbitrary type. You specify you generate E, which is, I am going to call gen type, oh, this has a derive checker. Sorry, this is not the, this is the one that's using it, that was shown before. So you're, again, generating an arbitrary type, and then you're using the derived checker, the derived generator, to produce an expression that's well-typed with some fuel of 5. Right? And then you're calling your preservation property that you defined above. So this plus the definition above is all you need to write in order to test your property. So where was it? Something like this. That's it. These 10 lines plus the derives that we wrote above is all you need to do to test preservation for SDLC. But coming up with those 10 lines automatically is like active research. So yeah, for now, you can get all the components, like how to generate things, how to type check things for free. And that's totally fine. You have to figure out how to plug them together. You have to tell QuickChick, well, I want to generate well-typed terms. Because if you just look at the definition, how does it know whether you're generating a well-typed term, or a type of the term, or an environment? Which one are you generating first? You have to make those decisions first. Yeah. So going back to the balanced thing, I think I deleted something too much. Let's hope I didn't mess everything up. But yeah, going back to the balanced, where is it? No. Yeah, going back to our automation thing, I think we were almost done. This basically shows the same thing, but for a particular property. So this generator does exactly what we did for preservation, but for balanced trees. It tells you that you want to generate a natural number, generate trees that are balanced, and then check whether they are balanced. And unsurprisingly, our generators are correct because they are also proved correct. So you get everything correct. And now let's write the property that we wanted initially, which was that insertion preserves balancedness, which means that if you give me something that is balanced, then I can insert something and it's balanced again, which will obviously not hold because, and this will obviously not hold because our insertion doesn't preserve balancedness, it just goes to the left. If you try to do this, you'll see something weird, which is that if you use, not really weird, like if this is the default generators, the way this works is just using QuickChick type classes, and it tries to generate an N and an X such that the tree is balanced. Well, if you try to generate trees that are balanced of size 5, you're never going to do that. Like if you generate an arbitrary tree of size 5, it's not balanced. No way, no how. There are too many non-balanced trees for you to do that. And in fact, we generated 20,000 random trees, and none of them were balanced at size 5. So what you need to do is write the test harness as almost by hand, which is generate me trees of the given size, and then they will be balanced. Then it's going to be fine. And now we get a counterexample, which is large because it's a balanced tree of size 5. But sure enough, if you try to insert the number 7 to this tree, you'll get something that is not balanced. You can try it by hand, that's not interesting, but yeah. but the trick is you get a balanced tree of height 5 immediately, where in the case where you're not using the fancy generators, you're just never going to get them. So I think we're almost out of time for the first one, so I'm not going to start the next part. The next half hour or so after the break is going to be a much more in-depth case study about binary search trees. So we've basically covered everything that we're going to cover in terms of these are the basic building blocks, and then we're going to see how to apply them to test binary search trees. In like, I think we only have like half an hour, 45 minutes afterwards. So yeah, break, right? Yeah. Yeah, it's fine. Let's go to the break early and continue after.
So this is, I thought my tutorial was twice. This is your.
No. It's like it's two sessions of the same tutorial, or not.
Oh, the same session.
No. I made that mistake in the previous. Oh, I was like, I had 1.5 hours, and then I was like, oh, they have 3 hours worth of service. Created it yesterday or something. Yeah.
One thing I'm interested in, is there any like sort of parachuting of characters that happen ever? So like, it seems like the sort of thing like there's a lot of human intuition.
Yes.
That in specifically like even just something as simple as just truth, like literally just the way it's putting in the weight of the size.
Yes.
And it has to be all like,
Yes.
like there is absolute sort of thing that
Yes. The problem is that any method that tries to do that, you can't really get any statistics out of it without running it as shit. Right? So like doing any kind of random walk to be like, oh, this way just gets me closer to a random distribution, we're going to like run like 10 million tests in order to get anything. So yes, you could tune it, but you need something you would leave over a weekend to tune. Whereas I would be like, yeah, I know I need to make that size.
So if you're going to be running over a weekend, you might as well just write it yourself.
Yeah, exactly. It's a very weird space.
I wonder if there's like, I guess I'm thinking like maybe you could do some sort of neurosymbol.
Yeah, like
There maybe you reduce the.
Yeah, so like that's one thing that we've been talking about probabilistic programming folks forever. Be like, for a lot of the cases, you don't want uniform distributions, right? Like if you have a uniform distribution of trees up to 5, all of your trees are going to be of size 5. Like that's not what you want. But you might want a uniform distribution of sizes in numbers of shards.
Actually, that was the exact question I was about to ask. I was thinking about this programming.
Oh, okay. Good.
I want to focus on E and Cloud and using it.
Nice.
Yes, and so Cloud has been working with automated external programs.
Okay.
Specifically with QuickChick as well, because so they have been working. He had this project where you would be like, oh, you want to test some work, you want to do something, and you want to come up with you're stuck somewhere that you want some kind of everything, but you are not able to, people get stuck.
Yep.
So, yeah, is there to that kind of data system which can determine possible
Okay, sure.
and what are feasible lemmas in that they use QuickChick a bit.
Okay.
Yeah. And then I was looking at this stuff while working with them, and I was like, okay, so they have these distributions, as I said. So, and then you mentioned that even after doing the parameters, we are not getting a uniform distribution. Because I guess there was 1600.
Yeah, you still had a lot of these. Like the the distribution you get is skewed by two things. It's skewed by the weight and it's skewed by your fuel. If the depth you're allowed to do is bigger than the fuel you're trying, like you're not like you're cutting things off. Like if you want a uniform distribution, the state of the art is just generate things this way and filter off anything that is not in your size. And that is stupid because I can still use that for testing, so why would I use that?
Right.
I've already spent the effort to generate them, so.
Right, but I was curious, like, people in testing community really care about having a uniform distribution.
Uniform distribution is actually horrible for them, right? Like it's really, really bad. Like my canonical example is something from non-interference. So there's a thing in security which is like indistinguishability. You have some secrets. So think about you have an entire machine, memory, registers, whatever, and every single location you have is tagged as either public or secret. Like I have access to a deal, something like that.
Okay.
And the idea is that if you start with something that only differs in public stuff, so all the public stuff are the same, and all the secret stuff are different, so I can see the difference, but you can't, then if I let it run, you still won't be able to see the difference. And that's like it's called non-interference, but the core thing is indistinguishability. The original machines are indistinguishable to you. What does that mean? I have an entire machine to like memory, insane amounts of memory, with 2 to the 64 possible integers, and each one that is public needs to be the same. So if you are uniformly distributed indistinguishable machines, they're just going to be high. Right. They're just going to be secret. There will be nothing that is not secret. Because for every single public piece of data, you have 2 to the 64 non-public. Yeah, good luck.
Exactly. So, like, I guess the solution to this that comes to my mind is if you can have a way of first having a uniform distribution over the public space.
So that's what the collect mechanisms sort of do. The idea in testing, at least, is you usually want a uniform distribution in stuff. For example, you want a uniform distribution of labels.
Right.
And if you condition on that, then it means that the other machine will have to be generated so that it has exactly the same label. Nice. Yeah, they have to be exactly the same, right? But that's really hard to generate. Like, probabilistic programming is not tuned for that kind of constraint something. There was like R2 or something by Microsoft that did something interesting in that regard. But it's really hard. So there's definitely a ton of room in terms of making sure that distribution is writing what you want, or being able to specify what they should be doing.
Right.
If you're, what's your name, sir? Nice. Yeah, I would love to talk about this. There's tons of things you can do in terms of probability for this.
Right, because like when I look at these generating test cases systems, the first thing that comes to mind is this is very limited.
Yeah.
Because I have a thing on the constraint and what is the method.
Yeah. And it's a very similar problem, but the difference is if you want to infer a distribution, you sort of don't care. Like you just generate the samples, and if you filter it, you fine, and you're inferring the distribution. Whereas if you in this, it might go. Yeah, it's not the one particular distribution. The conditioning that you're doing is very abrupt. Like I want well-typed terms. You're not going to get that by randomly sampling terms and then inferring the distribution of well-typed.
Correct.
Just not going to happen. So there needs to be some constraint solving involved, which completely destroys any notion of distribution that you had to begin with, but at least you get something useful. And reconciling those two things, extremely hard, extremely interesting, nobody does that. So if that's something you're interested in, that's a lot of stuff.
Yeah, definitely.
But I would be Okay, it's about time. Let's give it 1 or 2 more minutes.
Can I ask about the software engineering aspect of this?
Yes.
How has this annoying thing where you change something, then you have to rerun through all your proofs?
Yes.
I'm thinking, I don't want to generate 10,000 things or something that I've sort of proven correct, but I also don't want to have comments.
Yeah. So I wasn't going to touch on that in this tutorial, but there are comments, like we're using comments to sort of avoid rerunning tests for everything. I don't have, where is that? That should be in the Software Foundations volume, probably. Yeah. So there is an aspect of this, but by the way, there is a Software Foundations volume for QuickChick, which you can look at. It's looked at by Benjamin a bit more, so the pros make sense, at least. Basically, there are these kinds of comments where's a comment like that? It explains things. So here. So for example, you have your tests and you can write comments with this question mark, right? Like an exclamation point, sorry. Where, okay, they're in a comment, but they can run. Like if I uncomment this and run it, it would work. And there are mutants. Basically, you can write stuff like this, where this is the correct way of writing compile. I think I have that somewhere in QuickChick without the QuickChick examples, multi-file notation. Stack compiler has it. Yeah, so for example, okay, let's do multi-file mutation, which is stupid. Here it is. Okay, so here's the definition. The correct version of the definition is x plus 1. And the wrong version of the definition is drop the plus 1. So you can write comments this way that are sort of telling you how to document your bugs, if you want. And there are also QuickCheck comments like this, which allow you to write your properties. And there's an external tool that you can run, literally called QuickChick tool. And if you point it at this directory, it will extract all the different ways to break your properties and all the different tests that you want to run and run all of them. That's also faster because it only re-extracts the things that it needs that change across different mutants, so it saves you a bit of time. But yeah, like we haven't figured out a better way of doing the software engineering aspect of things.
But still, I mean, this is at least one step above manually commenting out.
Oh yeah. Manually commenting out would be insane. I think that if you're working on something and you want to document your tests, this is extremely easy to do. If you want to do this sort of, we have mutants to make sure that my tests are good and everything, it needs a bit more effort. I'd love to talk about that and fixing the documentation for that if you want, but yeah. Okay, I think we're here. So most of the second session, or at least the biggest part I have prepared, is a big case study on doing everything we've been talking about for binary search trees. Yes.
Are you online? There used to be a thing that said you were sharing your screen.
I am sharing my screen.
Yeah.
I just figured out that I can minimize it. Important. And I think the session is working. Yes. Nobody's online, but it's fine. Okay, so once again, we're going to work with trees because I wanted everything to be with the same data type. So we have trees, leaves, and we derive both of the things that we've said we've been deriving. And the precondition that we're going to look at is binary search trees. So it's one of the canonical examples for something that is both simple to understand and annoying to test. Okay, so what is a binary search tree? So here is a predicate, a function that characterizes whether something is a binary search tree with elements between low and high. So basically a leaf is always a binary search tree, and a node is a search tree if X is strictly in between low and high. The thing on the left is a binary search tree with elements between low and X, and the thing on the right is a binary search tree with elements between X and high. So you split everything on the left, split everything on the right, and everything works out. And here is an insertion function for binary search trees. It might be faulty, it might not be faulty. You might be able to spot it, it might not. So it just traverses the entire thing and inserts the element at what should be the correct location. So how do you write that? What property do you want out of this? The easiest one is you expect that if you insert an element to something that's a binary search tree, it remains a binary search tree. So you insert it at the correct location. And implication is one way of writing properties with that treat those if this is a binary search tree and treats it correctly. So it takes a Boolean predicate, like is BST, and combines it with the property that you want to check. So here is the specification that we care about. It says that if low is less than X and X is less than high, and the tree T is a BST with elements between low and high, then if you insert that element into the tree, you get a binary search tree with the same range, right? That should work. And sure enough, if I run my spec, I will get back a bug. And you'll know that if low is 0, high is 4, and X is 1, and my tree is node 1 leaf, then I'll get something wrong. So what's the problem? The problem is that X and the thing in the node are the same thing. So when you're inserting an element that is already existing, you're ignoring it. You're inserting it on the left. So you're keeping multiple copies of the thing, which shouldn't happen. So the correct way is to fix the bug. So you can take into account the fact that that the tree might be, so X is less than X prime, then you insert it. If X is greater than X prime, then you insert it. Otherwise, you leave it identical. That's the case that we were missing. And now the same thing with the insert spec. We can try again. And sure enough, it's gonna give up. Why is it gonna give up? Because it's generating trees in the most naive way possible. Right? It's generating arbitrary low, an arbitrary high, an arbitrary X, an arbitrary tree, and then hoping that this, and this holds. Right? So obviously it's gonna, like, I'm more surprised that it passes 1,300 tests than it fails 20,000. And the reason it passes those is probably like 1,000 of those tests are leaves, right? Which are always binary search trees. So we need to do better. And the first thing we can do is write a binary search tree generator by hand. And we can do that. Let's try and do that. So what was the approach that we were taking, right? We don't have an inductive to derive from now. So, well, you match on the size. That's the thing we said we would do always. What do you do when the size is 0? Well, the only binary search tree of size 0 is a leaf, no matter what. So you return gen a leaf, and you're done. What if it's successor of some other size? Well, now you have an option. And the first option is returning a leaf. And let's make sure that this compiles. Let's see. Do I need 2 for the notation to work? Okay. And the second case, is going to be something with generating a node. How do we generate a node? Well, we can. We need to do something now that generates a binary search tree with elements between low and high. So what would we want to do? Well, we want to choose something that is between low and high. But choose is inclusive, right? So you want to make sure, so you don't want to do low, high, because that might generate low or high, which is not strictly between them like you want. So you want to generate from something that is +1 or -1. But that might not be ordered, right? And you don't want an OCaml exception, which I showed you way earlier. So what you want to do is sort of check if, even beforehand, if low +1 is greater than high -1 or something, then you only generate a leaf. Otherwise, you have a choice between generating that, and you're already probably getting annoyed by the whole bind gen situation. At least I am. You generate a binary search tree with elements between low x with some size prime. That gives you the left subtree. Do the same thing for the right subtree, but with elements between x and high. And then you're putting everything together by just saying return gen node XLR. Close a whole bunch of parentheses as if we're doing Lisp and write it. And like, I promise you this works, like if you do gen sized, but I've also written the exact same thing in more convenient notation, because you can use notation to make your life easier everywhere. This is exactly the same thing, only instead of writing return gen, you write ret, which is part of the monadic stuff in, I think, Greg's library for monads. You have the same check, and instead of using writing bind gen and having a ton of parentheses everywhere, you just have cute monadic notation that reads exactly the same way. Like, you bind this to generate X, you bind this to generate L, you bind this to generate R, and then put them all together. It's exactly the same thing that we wrote above, it just uses a more convenient and readable notation, because I was already tired of looking at the thing above.
In the previous version, you had the question mark and the conditional after.
Yeah. So this is a matter of what you're using. Like, the only difference is that this is a Boolean check from Coq standard library. The other one was using the decidable instance for less than, based on type classes. It doesn't really matter, right? Like, they obviously are equivalent because they're giving the same result. I guess this might be a tiny bit more efficient because there's one less type class lookup, if you care about that much, but yeah, it's a matter of style. Like, at this point, I think I'm more tempted to use the postfix question mark for everything, because it's easier to read for me. Like, everything is inductive and I just put question marks and everything works. For a single check, it doesn't matter. If there were multiple checks, so if you go back to basic usage, .v not-block, EQ tree, like here, this is starting to get annoying, right? Whereas this is less annoying. So that's why I'm tempted to opt for the question mark everywhere, because then I also don't have to remember the name of BEQNat or whatever. Standard type class benefits. Like, it gives you modularity in terms of you remember one notation, not 12 functions. Okay, but we have this, and now we have to write the checker. Again, we have to write the thing that brings everything together. And what we're doing here is we're generating an arbitrary low. we're generating an arbitrary height that is bigger than low, because we want to make sure that that thing holds. We are generating an arbitrary x in between the two. We're generating an arbitrary trig t, and then doing everything. And then checking the binary tree. And now if we check this, we passed 10,000 tests. Fine, everything worked. However, we still had to write this thing, which, yeah, I wrote it like 5 minutes. But you can imagine that a lot of things would go wrong if you were trying to write it on the first try. And the things that would go wrong is, I immediately went for this low +1, high -1. That would have gone wrong. I immediately went for the check for if, which you would have gotten an exception here. And like, there are a lot of things that can go wrong when you write a generator. And we have this machinery now that we saw in the previous hour that allows you to derive such things. So let's see how they fare for that. So how would we write, could we do the same thing using the automation? And the answer is yes. So instead of writing a generator, you could write the inductive version of the whole thing and try to derive it. Usually, actually, you already have the inductive available. Like, nobody writes the checker version of BST first. But okay, let's say we have less than, and we have BSTs. So the way we have BSTs is, again, low and high. So a leaf is a valid binary search tree with no matter what the low and highs are, and a node is a valid BST if x is less than low is less than x is less than high, and the two things are recursively the same. Right? So the exact same thing I wrote as a checker, but in an inductive form. And now we can try to derive a generator for it. And because there is a fail, it should tell you that something is wrong. And this is one of the things that we need to fix, that the exceptions are a bit annoying. So what it says is that there are no checkers or producers for relation LT. So think about how this would be generated, right? When you're trying to generate this, okay, I can generate a leaf, that's one of my choices, or I can generate a node, fine. In order to generate a node, I need to generate a left, a right, and I have to do something about these things. Right? I have to make sure that the x that I generate is between low and high. But the LT relation is something that I just defined above, right? So QuickChick doesn't know how to generate these. QuickChick doesn't know how to test this. So it needs to do something about it. And the idea is that, okay, you have to go and derive things for it. So what do you derive for it? Well, let's try to derive the checker. So we derive something that checks whether n is less than n. And sure enough, that works. And you can look at it to see what it does. It's exactly what we saw in the last session, where you're, let's have this on the side as well. Basically, it says, okay, is my second number, my first number 0 and my second a successor? If so, first number 0, the second a successor. If so, we're done, sum true. What about the other way around? Are both of my numbers successors? In that case, I will do a recursive call. So it's literally just trying to satisfy this inductive. And now, after you give me that decop, QuickChick is happy to generate a generator for binary search trees. That should start yielding some red flags, because it still doesn't know how to generate x's that are between low and high. It just knows how to check whether x is between low and high. So what are we going to do? Well, let's write a generator that calls our function. And again, we have to write the whole, how do you generate the different things and fit them all together? So you generate an arbitrary low like before, arbitrary high like before, arbitrary x in between the two like before. And the only thing that's different is that we're calling this generator, which uses the derived generator to generate our tree. Right? That's the only line I changed compared to the thing we had above. And then I check with the checker that we had before. So I'm just using the function to check whether it's a BST. And sure enough, if I run it, I get 10,000 tests. Are we done? Like 10,000 tests pass, we should be fine, right? But most of the time when you see 10,000 tests passing, it's either because you did such a great job and everything is fine, or your generator is doing something stupid. Sampling your generator is a very good way of seeing if you did something stupid. And we actually got some notes here, but when I ran it 3 days ago, I got only leaves. Why would you be getting only leaves? Why would you be getting this small window of generation? Well, let's look at the generator itself and try to figure it out. So if we run this, it tells us the name of the thing it generated, size such that BST. So here it is, and here is the thing it does when it, let's copy it and have it somewhere that's readable, assuming that's a thing that it can be. Okay, so what does it do? Let's try to reorganize it a bit. It is largely readable, but we would need to do to convert things to an arbitrary, to a bind notation. So, okay, this generates an arbitrary x. Then it checks whether x is less than, low is less than high. So basically it checks whether low is less than high here. If it is, it checks whether x is less than high. Generate arbitrary x. Check whether low is less than x. Check whether x is less than high. And only then does it keep going to generate the rest of the tree. If it doesn't, if any of these two checks fail, so if this returns false or this returns false, you return none. And then based on backtrack, you're going to backtrack and return a leaf. So basically what you're saying is that you're trying to generate a random element between a low and a high value randomly. And if you can't do that by generating a random element completely without taking those values into account, you're going to generate a leaf. Yeah, you're always generating a leaf. After all, like that's why you're passing 10,000 tests. So one thing you need to do in cases like this is try to figure out what's going wrong. And the very first thing is the way QuickChick generation algorithm works is that if you have some generator for less than, it will try to use that first. So if this is just a matter of removing the type class instance for the thing that we just generated. But if you also derive a generator for less than, so this derives a generator for x's that are greater than n, then the generator that will be produced for BST, such that BST0, is not going to start with generating an arbitrary x. It's going to start with generating an x that is greater than low. So that's already fixing half of our problem. Not all of our problem, because it still doesn't take high into account, but it's already going to be much better than before. We're generating some much larger trees and so forth. How do we quantify that? We can't just look at 11 values. Right before, we want some way of calculating size, and then we can add this collect incantation to our checker from before. So we give it a generator, and it will tell us how many things are of what size. So the original one, the one that I said was really bad, out of 10,000 tests that we passed, I think 500 were leaves. Yeah, so that's why it was passing. On the other hand, for the new one, perfect. What happened? Okay, I've never seen that bug before, so that's scary. Oh, I know what it was. So software engineering, I'll say what happened later. But this is still bad. Like, still a lot of things are, at least we're getting some trees of size 3. Not a lot. So why is this still bad? Well, it still checks whether x is less than high, right? It's not whenever you're generating an x here and making sure it's greater than low, well, 42 is greater than 5, but if you wanted elements between 5 and 10, you have way more elements that are greater than 10 than not. So you're still going to be discarding a ton of them. And here is when I'm not sure what the correct approach would be, but one approach would be, well, instead of specifying them as independent constraints, specify them as one. Merge them together. So you could define, instead of having them as low and high, you could define them as between. Right? So here's a between function that says that when three numbers are ordered as this is less than this, less than this, it's not too interesting. Basically, zero successor event is always in that relation. You can add something to the last element, or you can add something to all three elements. And that's a way of constructing all things in between. And now I can write a BST prime that has this relation at hand. Fine. And therefore, I can now derive a generator for x's that are between low and high, and now a generator for BST prime. Now, what happens if I use that to collect things? Well, much better. I'm trying to generate trees with elements between 0 and 10, and I'm getting like 200 trees of size 5. That's basically the limit of how many trees fit in that range. But is it as good as the original that we wrote by hand? Well, let's see. The original that we wrote by hand was even better. Why? Well, the original one had this thing, right? The original one was checking if low plus 1 is greater than high minus 1, and in those cases returning something, whereas this one was failing. So, and the second thing is that the distribution of the thing that is produced here, so gen size such that is prime, the distribution here is 1 and 1, as I said, right? Like the default distribution that it picks for weights is 50% leaves, 50% something else. Whereas before, we skewed it much more towards the size. And now, as I promised way in the beginning, this actually does work in this file, where, wait, let's go all the way there. Instead of deriving just the thing for BST, you can write this incantation that says that, oh, whenever you're trying to generate for the BST leaf constructor, use weight 1. Whenever you're trying to generate for the BST node constructor, use size as the weight. So what that will do, again, size such that BST prime 0, it's going to have this distribution induced. So it's going to use 1 for the leaf, and size, which happens to be successor of size prime, for the node. So you can hijack the generation process and tell it what sizes to use.
And size here, is that magical? Is it because it's the name you use?
Size is a special thing that uses the size because it's a very common thing to do. Basically, I think the default works with numbers and size and expressions over those. So you could do size times size or stuff like that. It's not hard to do more things, but it's usually not what we do, so we haven't implemented that. But like, the way this works is this registers a flag in a table that says that whenever you're doing the weights, just use these. You can just use these assuming they're in scope. So, depending on how fast and loose you want to play with this failing, you could allow arbitrary expressions there.
But if you said SZ, for example, then it would be...
No, that wouldn't work. Expected number or size. Right. Yeah. We fixed some of these error messages. I don't know when that happened. They used to be much worse. Yeah, so if you do all of that stuff, And now the distribution is basically identical to the one you had before. So the point here is not that you should be hacking your inductives in order to get your performance, is that the way you write your inductive, unfortunately, still matters for the generators that you get from QuickChick. So I've been sort of talking about a lot of possible things that we need to fix in terms of automation and stuff. The second thing is, the other thing we need to fix is that, well, the BST we had above and the BUST we have here, where is it? Here, okay. Here are the two search trees. They are very similar, right? This and this differ only in one very tiny thing. However, their behavior in terms of derived generators is completely different because this has a much better behavior. How could we get from here to here automatically? Not me looking at this right now, it's like, yeah, just merge these two together and get it. Maybe that will work in a bit. What if this was later on? What's the problem here is that you're instantiating some things way too early. Right? You're instantiating X without taking this into account. But it's not always that you want to take every constraint into account, because low less than X and BSD low X null, that's fine. It's fine to generate X here and ignore the constraint on the left tree. But it's not fine to generate X here and ignore the constraint on high in terms of generation. So again, arbitrary problems inside constraint solving for this. I have no idea what to do, but the point of this exercise is that there are things you can do to sort of get as much performance as you can out of your BST. So, out of your generator. So just to recap the main things. By the way, all of this is available in two forms. In the Software Foundations volume, it has a lot of these things. And these are examples in the QuickChick repo itself. The main thing to keep in mind is whenever you're defining an inductive, you can derive arbitrary show, and that will give you a generator, a shrinker, and a printer for that thing. The next thing is if you're defining an inductive definition for whatever you want, like, where's the BST? Here, you can derive generators, checkers, and shrinkers for this, but you also need to derive checkers and generators for the other relations that appear inside it. And QuickChick will automatically figure out the best way to link those together. So if you give me just a checker, I'll check everything. If you give me a generator and a checker, I'll generate things as much as possible. And the order of these constraints matter. So if you happen to move this before the LTs, that would also be annoying because you'd have to generate X before we were checking this. So as a rule of thumb, write your inductives for the simple data types, derive, show, and arbitrary. Write your constrained inductives that you want to generate for, like you would normally do. And then try, the rule of thumb is try to put the most constraining things first. The things you want to generate, you would generate first by hand, put them in earlier on in your data types. I don't know of a way that we could make that better, right? Like if you have any ideas as to how, given arbitrary relations and constraints here, you would reorganize them to get the best generation performance, that's an arbitrary hard research problem, almost. And then after you generate those, you have to write, the thing you still have to write that is annoying is these things here. This is the glue that ties everything together in terms of how do you generate the various things that your generator takes and your checker takes. You generate a low, you generate a high, you generate an X, you generate a T in this particular fashion. And then you check the whole thing. This is in the process of being automated, but not yet there. Everything else so far is almost mechanical. So you can derive everything else, write this way that links the glue together, links everything together, and you get checkers for your BSTs, and as you saw for the STLC and stuff, for free. This is obviously a research artifact, so there are still times where it will fail. If you have any cases where it did like that, just send them my way. We'll fix them, hopefully. But the rule of thumb again is, if the standard induction hypothesis that you get from Koch for the simple data types or for the BSTs and stuff would work, like it would be useful, then this will work. Then this should work. Anything non-regular, if you're having nested lists of trees as your example, or fancy mutually defined data types, the algorithm behind this can handle it. The software engineering that we did can't, right? So we haven't encountered those as use cases, but if you do encounter them, I'd be happy to tackle whatever it is. Okay, I think the last half hour that is left, I had set out for sort of debugging and demos and anything like that, and I was thinking that this would last a bit longer. But are there any questions or anything like that? Oh, I still owe you an explanation for the bug. Yeah, so the way QuickChick works is whenever you're compiling something like this, there is this thing in my temp folder, which are being generated. So these are timestamps. So the things that we were just doing are on like 11:37 something. So 11:37:47, for example, was the last thing we did. And whenever you're doing a QuickChick command, whenever you're doing one of those samples or one of the QuickChick commands, what happens is this thing is being created. It's a very pretty file. 700 lines is on the small side. And at the end of it, it's a QuickChick call. So it extracts everything into a single thing and tries to compile it. Now, what happened when that said, it said that there are already artifacts, which means we happened to hit the exact timestamp of one thing I did like yesterday or a month ago. And it tried to compile two things in the same file that was already built, and it failed. So every once in a while, you need to... Yeah, they're not good timestamps. Like this is not a very well engineered software engineering project. I'm surprised it works as well as it does, but there are obvious deficiencies, right? I think the end goal for not the too near future, but like in 2 or 3 years, I'm hoping you can just write QuickChick in the middle of your proof, and everything just works. Like it figures out what it needs to generate in what order, how to derive the things it needs to generate for that order to work, how to link them all together, and how to check them. Like the different components for that sort of already exist to make a best effort. So it's going to happen. The problem is that I don't know of a principled way to do that. Like I can hack something together that just tries a couple of things and makes a best effort, but that's not going to work well in many cases. So trying to get that exact thing working is the next step, and fixing the engineering of it. Okay, any other questions?
Yeah, can you show the between predicate again, because I didn't understand.
Yes.
How can you show that between 0 to 3?
Here. So 0 and 1, this is 3.
That's between 0, 1, 2.
No, this is n. This is an arbitrary n.
And
Yeah, so you can.
I see. Okay.
Yeah, you start with a number at the very end, and then you can increase it as much, and then you can.
I should have been sitting closer.
Yeah, yeah. One thing that's cool and might work. Wasn't planning on doing it. Staff. If you go to a different branch of QuickChick, recompile the whole thing. Compiling QuickChick takes a while. Not expected to take this long time. Oh, I'm not plugged in well? I don't know. Anyways, almost done. A new feature that, before we even go. What? Oh, warnings or errors. Fine. I'll fix that after. If you go to QuickChick, there are tons of branches and tons of things that are going on. The current version that is actively working on being released, and the one that works with a QuickChick book, is the 2.0 beta. We're making a few, and everything I've been talking about is in this branch. Like the entire thing I was working, it was here. At some point, hopefully this semester, before the summer, we're going to actually release the 2.0 with all the changes. But basically everything, all the derived fancy generators I was showing, they're all in a revamp of the code base that allows you to do that. So if you want to play with the constraint stuff, you need at least the 2.0 beta, or whatever release comes after. Because if you just install it through Open, you won't find them. Yeah, and that should happen relatively quickly. There are other branches here that are very, very experimental, and one of them that I was trying to compile, but I wasn't prepared for, so it's probably still broken, is this merge ins, which allows you to take the less than relations that you saw and combine them to between on their own. So you could automatically go from the version of BST to the version of BST prime by automatically merging things. But yeah, I can't fix the build for this now. Cool. And with that, I don't think I had anything else. Any other questions? Then let's break for lunch 15 minutes early. Thanks.